All right, so this chapter is path and trajectory planning. So I won't be doing path planning. I don't think we can do that. We don't have too much time. And but trajectory planning is more important. That's why I decided to do the trajectory planning. Okay. So what is trajectory planning? So you know what trajectory is. So in this chapter, trajectory meaning time history of position, velocity, and acceleration for each degree of freedom in the robot. Okay, for let's say for each joint, right? We have a joint variable. For each joint, we have each joint could be either prismatic or it could be revolute. So for revolute, we have the angle, right? And for the angle theta, and for the prismatic, we have D, right? So how does that D change with time? Okay, so how does the position change with time, or velocity change with time, or acceleration change with time? Similarly, if it is a revolute joint, how does the angle change with time? How does the angular velocity change with time? And how does the acceleration change with time? So we have to do that for each degree of freedom, for each joint, one at a time. Okay, so from initial point to final point, how does each joint move? Okay, that's what we'll be doing in this class. Okay, so not only that, it has to go from initial point to final point in a smooth manner. Okay, that's the otherwise you don't want to have a jerk, right? So it has to go in a smooth way. So we have to have that in a smooth manner. So how do you do the smooth? How do you make the trajectory smooth? So what is smooth actually? What do you mean by smooth? In terms of math, what is smooth? We know what smooth is in layman's language, right? But in terms of in mathematical language, how do mathematicians understand when we say smooth?
Slope.
Smooth. Yeah, smooth meaning is the function is continuous, right? The slope does not break if it is first derivative. So meaning smooth means it's continuous. The function is continuous and its derivatives are continuous. Okay, suppose you have a function like this. So like this, right? Then this function is not smooth because there is some discontinuity here. Okay, it has to be smooth. Okay, continuous. The function has to be continuous. Not only the function, the derivative of the function should also be continuous. So sometimes not only the first derivative, sometimes you desire the second derivative also continuous. Okay, mainly function itself and its first and second derivative are continuous. In that case, our function is said to be smooth. Okay, that's what we meant by smooth function in terms of in terms of mathematicians' language. So the thing is, when you go from first point or initial point to final point, okay, it goes through sets of via points. Okay, so there are several via points in between. Maybe this is one of them. Maybe this is the other one, right? So smooth function, any smooth function of time passes through the via point could be used to specify the exact path of the exact path shape of the robot. So in this chapter, we'll discuss a couple of simple choices for this function. So when we say smooth function, we have a couple of choices. Okay, so that's what we'll be talking about. Okay, so now our goal here is we want to plot the function as in space time. Okay, space and time, meaning in your x-axis, you have time, right? Then in the y-axis, you have, it could be, you know, q. This q could be d, or this could be qb. Q can be theta, okay? In the case of revolute, this q is theta. In the case of prismatic, this q is d, okay? So that's our goal. So we have to plot the graph in time, space time, okay? Q, which is space, and t the time. And this has to be done for each joint angle, okay? For each joint angle, we have to do that. So in other words, a small smooth function is found for each of the end joints that pass through the via points and end at the goal point, initial and final point, right? Final point, which is also called goal point. The time required for each segment is same. That's very critical here, okay? So that's the only constraint we have used here. Other than that, each of the segment is independent. Okay, we have to do this calculation for each joint independently. But only constant is that the time required for each segment is same. Okay, so if the, suppose one, you know, this guy, this is segment number 1, this is segment number 2, but you have robot, right? So I would say joint rather. So this is joint 1, this is joint 2. So this is the final point for joint 1, this is the final point for joint 2. We are moving our robot from this location to that location, right? Then in that case, what is the time for this joint to reach the final point from 1 to the, you know, let's say this is, I don't know, let's say 3. So what is the time for joint 1 to reach point 3? That is t, right? If this is the t, then exactly during that same time t, the joint 2 reaches the point, let's call 4, number 4. So this time is exactly same. So that's the only constraint we have imposed here. Other than that, we deal with all the joints independently. Okay, so meaning we do the calculation independently for each joint. Okay, so let's say this joint is defined by theta, right? This the joint 1 is defined by some angle theta, joint 2 is defined by some angle theta 2. So this is theta 1, this is theta 2. So we do the calculation for theta 1 and theta 2 separately, but keeping in mind that the time required for each segment is same to reach the final point or goal point. Okay, for most part, we will consider motion of a manipulator as a motion of tool frame relative to the station frame. Okay, we express the tool frame relative to station frame. That's what we will do most of the time. Okay, so what I meant by tool frame and station frame, I'll show you a picture. I think that will be, from the picture, it will be very clear. Okay, so in the picture, you can see here, right? This is a robotic arm, and your arm has some functions to do. This is your workspace, and this is the station frame right here. This is the station frame. Okay, and this is the tool frame. That's what I'm talking about. Okay, so we express tool frame with respect to station frame. Okay, all right, so now the thing is, when you plan the trajectory, right? So there may be some constant that you have to take into account. Okay, for instance, so you can have the constant like this. Okay, my robot must start and end with 0 velocity. Okay, if that is the constant, then how do you do the trajectory, right? How do you plan the trajectory? What kind of trajectory you have to have in that case? What kind of function you have to have? That's what I meant. So is it quadratic, or cubic, or fifth power, or I don't know. What kind of function do you take if we have constraint? Okay, so depending on the constraint, we have to take one or the other kinds of function. That's what I'm trying to say here. Okay, so if you have let's say n constant, right? Number of constant equals n, then you have to use the polynomials of degree n. Okay, that's what I'm trying to say here. If you have 4 constant, then you have to choose the polynomial accordingly. If you have 6 constraint, then you have to use the higher order polynomial. So in this case, I have just 2 constant here, right? The robot must start and end with 0 velocity, meaning the initial velocity is 0, right? And final velocity is 0. Those are the 2 constraints. Okay. Sometimes we might have more than 2 constraints. So sometimes 4 constraint, sometimes 6 constraint. Depending on the constraint, we have to choose, the function accordingly. Okay, you have to have the higher degree of polynomial. If you want to choose to represent your function by using polynomial, then depending on the a constraint, you have to use different polynomial, different degree of polynomial. Okay, that's what I meant. Okay, now in this chapter we'll consider at most 6 constraint. Okay, when the robot moves from one point to the other point, we might have at most 6 constraint. Okay, so we are going from initial to final configuration. While doing so, we have to satisfy the constraint, such as velocity, constant on velocity, constant on position, and constant on acceleration. It could be linear or it could be angular, depending on the joint. Okay, so in this case, we will do this for one joint, right? So there is an example here. After a couple of slides, I have one example. So this example consists of just only one joint. Okay, so we can do this. You can repeat for other. And if you have more than one joint, then you can repeat the same process again and again and again. Okay, so that's why I did not label anything here. I did not say Q1, Q2. If you have 3 joints, right? If you have 3 joints, this is joint 1, this is joint 2, this is joint 3. Then you have to have Q1, Q2, Q3. Okay, so you have to do the same thing for each of them. But I did not put anything here, 1, 2, and 3. I simply dropped it because this is valid for any joint. Okay, you have to do it for each and every joint, one at a time. So what are the constraints we will be considering in this class? In this level, we'll be just considering the constraint in the position. Okay, when I say position, it could be, it could be Cartesian, it could be angle, right? Okay, so meaning in this case, the initial position is Q0. Okay, my robot has to go from Q0 to QF. That's the constraint. Okay, this is constant 1. This is constant 2. My robot has to go from position Q0 to QF. Okay. Similarly, my robot has to have initial velocity of V0, and my robot has to have final velocity of VF. So in total, we have 4 constraints. Then my robot should have initial acceleration of alpha 0 and the final acceleration of alpha f. Okay, when I say alpha, this could be either linear acceleration or angular acceleration. Okay, it could be either one depending on what kind of joint you have. Similarly here, velocity, it could be linear or angular. Similar displacement, linear displacement or angular displacement. So we can have at least at most 6 constraints in this course, okay, in this level. So now our main goal is, so let's say this is our starting point, right? I'm doing this for joint 2 here. For this joint 2, okay, my Q is theta 2. So I can do same thing for joint 1, but I'm not doing it right now. So I'm doing it for joint 2. So this joint, this is your starting point, and this is my goal point or final point. My robot has to go from S to G, starting point to goal point, okay, starting to end point, okay. Then when the robot does so, it has to go through some via points or via points here. So those are the via points, 1, 2, 3. So you want the robot to go through those points, okay, because there could be some kind of obstacles there, right? So this kind of obstacles in between. To avoid the obstacles, you don't want to go your robot randomly from S to G. You want the robot to follow some path. Okay, that's what we'll be doing. All right. Now this trajectory planning could be done in 2 ways. One, the joint space scheme. The other one is Cartesian scheme. Remember when we did the, help me here, what is that? What do we say? Yeah, tool frame, right? Okay. So, okay, so when, so how do you represent the point of the, how do you represent the position of the tool frame? Okay, so it could be in Cartesian scheme, we can represent by x, x, y, s. That's the starting point, right? If you see here, so what is the coordinate of s? Coordinate of s is xs, ys. Okay. Similarly, coordinate of g is xg, yg. Similarly, these points also have similar coordinates, right? That's what I meant. So these are the coordinates for each of the points in Cartesian system.
How would you even find the coordinates in real life? There's not like an XY frame we can just base off of. We use like a ruler.
Yeah. So because this is your frame.
So we say like what, like 7 inches to the right, 12 up, something like that.
Yeah. So, but the thing is, but in real life, you don't do that, right? You don't put the data. You just make the function. Okay. So that function can take care of any x and any y.
Yeah.
Right.
But then again, how would the robot know and move that space? Like, how would it know it moved 12 inches? It would just go by like a timer.
Yeah. Okay. That's okay. That's a very good question. All right. So what you have to do is, instead of doing x and y, right? So we do it in terms of angle theta, which is much easier. Okay, that's what we do most of the time. That's what I'm trying to take you guys right here, okay? So we have 2 kinds of scheme, which is Cartesian scheme and joint space scheme, okay? In the joint space scheme, your theta 1 goes from theta 1s, theta 1, 1, theta 1, 2, theta 1, 3, theta 1, g. That's your theta 1. That's how it goes. In the similarly, theta 2 goes from theta 2 s up to theta 2 g. That's how it goes, right? So our goal is, so how does this theta 1 go from s to g? That's what you will be doing, okay? Similarly, after you finish theta 1, then you will be doing this also. Depending on how many joints you have, you will find a scheme for each of the theta, each of the angle in this case. I think I'll answer the question in a couple of slides, Almes, if I haven't already answered.
And well, I just remembered like yesterday when I was working on the robotic arm, I'm kind of doing the Cartesian scheme. Like I know 500 is the left and I know 2,500 is the right. That's the workspace. If I want in the middle, I go 1,500. If I wanted to move my wrist a certain way to like the 700 position, I put it in an equation like that.
I think eventually if you
but I'm thinking of a better way of doing it because it's a little like it's not smooth because the way that the Arduino puts out the data is not fast enough,
okay.
and it's choppy. It's not a like smooth thing like you were talking about earlier.
Yeah, so we'll figure out how to make it smooth.
Yep.
Yeah, so we'll figure it out. And the thing is, we don't do it most of the time. We don't do it in the Cartesian scheme, because remember when you define the motor, right? So you have the joint here. So each joint has a motor, right?
Yeah.
Okay, each joint has a motor. So that motor is specified. Motor is controlled in the joint space, not in the Cartesian scheme. So they are defined by angle. Okay, that's why we most of the time we do joint space scheme. This is scheme, not that scheme. So I highly discourage you to not use this scheme, because eventually, since motor, we just talk about the angle for the motor, right? So that's why you have to convert back to, even though you do in XY, okay, you might have to go back to theta, which is inverse kinematic. So in that case, if you do Cartesian scheme, that will be computationally expensive.
How would you measure that? Like a protractor?
Yeah.
Okay.
Okay. So now let's do how to do the smooth curve for theta 1 now, for instance, right? So first of all, let's finish theta 1, then we will do theta 2 also. Okay, so our goal is to finish this up. So all theta goes from theta 1 goes from theta 1s to theta 1g, like this, via point 1, 2, and 3 in my case. So once we're done with the theta 1, we can do the similar thing for theta 2. So while figuring out a smooth function, make sure so your first and second derivative also continuous. So when I say theta, at the same time you will be doing derivative of theta and second derivative of theta also. Otherwise your function won't be smooth. Okay, make sure your first derivative is continuous, second derivative is continuous.
Is this another way of coding the robot motion, or do you still have to do like the inertia and Jacobian thing too?
No, you have to combine all of this. This is just to make the path smooth. We are trying to make the path smooth. Otherwise,
that would be so much code to put all the stuff that we've done so far into one thing.
Yeah, see, in this case, how these paths, when your robot goes here, right? So it has to suddenly turn here. So that gives you jerky motion, right? That's not what we want. The whole idea is how to make it smooth. Okay, that's what I'm trying to do here. Okay, so to do that, we have different options here. One is cubic polynomial trajectory. We can use cubic method, quintic, which is a polynomial of order 5. Cubic, obviously, polynomial of order 3. And quintic is the polynomial of order 5. Okay. Then we have a linear. We have the linear, but with parabolic blend there. Okay, we put the parabolic part in the end. Suppose you have a function like this, and in the end you make a little bit parabolic like this. Similarly, here also you make a little bit parabolic like this. So that's your this part, linear segment thing. So we'll be talking about each of them separately, one at a time. So let me begin with cubic polynomial trajectory. If I do this, I hope it makes more sense. Okay. So when I say cubic trajectory, we have the cubic polynomial of this form. So where q is, it could be, again, this q could be d or theta, depending on what kind of a joint you have. In the prismatic, you have d. For the revolute, you have theta. So your q could be d or theta. So that q is, if it is cubic polynomial, then the general form of cubic polynomial is this, right? This is my general form. It goes all the way to 3, t to the 3. That's what cubic means. Now, how many constants this trajectory can handle at most? It can handle 4 constants. It cannot handle more than 4. Okay, so using that 4 constraint, you can figure out A0, A1, A2, and A3. That's my final goal, right? So we have to find, remember, y equals fx, right? Y equals fx, or ft in my case. Okay, ft. Okay, so y is q here, y equals ft. So you have to find t is variable, and y is also variable. Now, there's A0, A1, A2, A3, these are parameters that you need to figure out by using these constraint here. If you have 4 constraint, then using those 4 constraint, you can figure out 4 parameters. Okay, that's what I'm trying to say. So let's do that, okay? So this is my given cubic form, right? So what happens if you take the derivative of this guy, time derivative, q dot, that's on the left hand side, and this guy, derivative of A0 is constant, so that's why it's 0. You don't have A0 here. Then you have a derivative of this guy, which is A1. That's what is your first term. Then you have to take the derivative of this guy, which is 2a sub 2t. And similarly, you have to take the derivative of this guy, which is 3a sub 3t squared. That's how you get the derivative of this guy. So we have the equation 2, which is the derivative of equation 1. Now we have 2 equations. Now let's use these 4 constant here in those 2 equations. Now, first of all, let's use these two constraint. Let's use these 2 constraint for these 2 equations. So what do you get? So qt0, my t0 is q0, right? Okay, qt0 is q0. That's why my left hand side is q0. Then a0 is a0. Then a1, when you have t0, then here also t0, right? So a1 t0, a2 t0 is squared, a3 t0 cubed. That's my first. Okay, so I have used this condition for in the equation 1. Now let me use this condition for equation 2. This is the condition for equation 2 here. If I do that, what do I get? Q dot T0 is V0, right? That's what I meant here. V0. Then A1, 2A2 T0, then 3A3 T0 square. I'm done with this guy. Now, similarly, I use this constraint again for equation 1. If I do that, then your left-hand side will be QT, which is QF. That's my QF. Then rest will be A1, A0, A1 TF final, right? Remember, this is my T is TF here. So then A2 TF squared, A3 TF cubed. Similarly, finally, I will use this constraint for equation 1, equation 2. Then you get this equation here. VF equals A1 plus 2A2 TF 3A3 TF squared. So 2 equations and 4 constraint, we have 4 equations. Does it make sense? Guys, help me here.
Well, oh, A's are the unknown.
Yeah, age, that's what we are, our final goal is to determine age now. We have to figure out age now, that's our goal. Once you figure out A, then I have the equation here, right? Y equals M, you know.
Q is nothing important. It's just a letter.
Yeah, Q is, it could be, it's the parameter, right? It could be D for the prismatic joint, remember?
Yeah.
And D and theta for the revolute joint.
And we add a different, we add a A1, 2, 3, depending on how many links we have.
No. This is just for the one link. This is just for the one link, okay? Single link. I'm just talking about single link. That link could be prismatic. In that case, my Q will be D. That joint rather could be revolute. In that case, my Q will be theta. Now here A0, A1, A2, and A3, because we want to model the trajectory, right? We want to model what will be the trajectory. What is the nature? What does the trajectory look like from initial point to final point, right?
And we're assuming cubic because it's going to be in that shape.
Yeah, that's what because generally we consider they are the most common trajectories here, okay? Cubic, quintic, and linear segment with parabolic blends, LSBP, PB. They are the commonly used trajectory method in robotics. Okay, so simplest one is cubic. So I have this, I use cubic here because I have in the cubic I have 4 parameters, and to determine 4 parameters I need 4 constraint. Those are the constant given. You don't have to worry about this constraint. This will be given to you, or you decide when you want to, what kind of robot you want to build, right? You decide it in the very beginning. Given means you decide it in the beginning. So once you decide, then depending on the constraint, you choose what kind of trajectory function you would like to have. If you have 4 constraints, then you cannot go below cubic. You cannot have quadratic, because in quadratic, you have 3 parameters, but you have 4 constraints to satisfy. That doesn't work, okay? At least you have to go to cubic here, because cubic have 4 parameters, then you have 4 conditions or constraint. So you have to use the cubic there. Does it make sense?
Yeah.
Okay, good. Now, so once you understand this, then how do you write this guy in matrix form? Can you write this guy as this? So let's go back, okay? So let's go back from here to here to make sure it makes sense. So this is just matrix multiplication. You have the, what is this matrix? This is 4 by 4. This is 4 by 4 matrix, and you have a 4 by 1 matrix. If you multiply this matrix with that matrix, then you have to multiply this way, right? So 1 times A0, that's my first one. Then T0 times A1, that's my second one. Then T0 squared times A2, that's my third one. Then T0 cubed times A3, that's my fourth one. And that should be equal to Q0. That should be equal to Q0 right here. Similarly, if you multiply this guy with this guy, then you get this equation. If you multiply this guy with that guy again, you get this equation. If you multiply this guy with this guy again, you get this equation in the same way. Now, if you remember in linear algebra, right? So when does this equation have the solution? What is the condition for non-trivial solution in linear algebra? So if you have the matrix like this, does this matrix have always solution? The answer is no. Okay, this matrix has solution only if the determinant, this determinant does not vanish. Meaning, if the determinant is not 0, then you can guarantee the solution. If the determinant is 0, then the solution is trivial. You cannot guarantee any. It could be. Sorry, I'll take it back. If the determinant is 0, then you have infinite, solution. That's not desirable. Okay, so to make sure you have the unique solution, you have to have the determinant equals to non-zero. Okay, if the determinant is non-zero, then you can guess from here that. So you have how many equations? You have 1, 2, 3, 4 equations. Then how many unknowns? You have 4 unknowns: A0, A1, A2, A3. If you somehow verify that the determinant is not 0, right? Then you can guess from here that you can solve these 4 equations, because you have 4 equations and you have 4 unknowns. Okay, so in that case you can solve equations, but how, we'll talk about it later. Okay, but at least you know this, you can solve it given that this determinant is non-zero. Again, that's the condition. So let's check whether the determinant of this guy is non-zero. So if you find the determinant, so you can do that. Okay, if you do the determinant, then you happen to find the determinant equals TF minus T0 to the 4. So is this guy is 0 or non-zero? If the time interval is non-zero, right? Meaning if your T0 not equal to TF, when T0 equals TF, it means your robot is not moving. So in that case, you don't have to worry about trajectory anyways, right? So when T0 is not equal to TF, this guy is never 0. It means the solution exists. Solution of these equations, this system of equation, we have 4 equations. The solution exists. So when you have 4 equations, then you can find the 4 unknowns, which are A0, A1, A2, A3. Okay, now you can solve these equations and you can find A0, A1, A2, and A3. Then once you find A0, A1, A2, A3, then you plug this in here. That's the trajectory of your robot for particular joint. Okay, so you did for particular joint. Now similarly, you have to do the second joint, third joint, depending on how many joints you have. Does it make sense so far? Let's do a problem. Guys, any question here, please?
I think it's pretty basic.
Yeah, it's pretty basic, right? Yeah. Let's do a problem here. A single link robot with a revolute joint is motionless at theta equals 20 degree. It is desired to move the joint in a smooth manner to theta equals 80 degree. This is your goal. You want to move the robot from theta equals 20 degree to theta equals 80 degree. So you want to make sure that happens in 4 seconds, sorry. Find a suitable cubic polynomial to generate this motion and bring the manipulator to rest at the goal. So now you see your 4 constant, right? You have Q0 equals 20. That's my 20 degree. And Q4 is 80. Then Q dot 0, in the beginning, the velocity is 0. In the end, the velocity is 0. Those are the 4 conditions. So we are going to use, again, this equation here, right? We are going to use this equation. Now, thing is, you have to just simply plug in the value of T0, Q0, V0, QF, and VF. 1, 2, 3, 4, and T0, 5. You need to plug in the value of 5 quantities, then 5 parameter rather, then you get this. So 1 is 1. What is T0? T0 is 0, right? T0 is 0. Then since T0 is 0, you have all of them 0 here, because you have T0, T0 squared, T cubed. Then this one is this one here. And what is your Q0? Q0 is 20, right? That's my 20 here. Similarly, 0, 1, 2, T0, both of them 0. So you have 0 and 1 here. 0 and 1. Then V0. V0 is 0, right? This is my V0, which is 0. Similarly, you plug in all those things and you get this equation here, this equation, matrix equation. Then how do you solve this matrix equation? I did it in MATLAB. You can do anyone, and it's so if I do in MATLAB, it's in very simple MATLAB. I don't know whether you guys are familiar with MATLAB. So this is what is, because my primary language is MATLAB. So most of the time I do everything in MATLAB.
Inverse A cross B?
Yeah, times B.
Oh.
This is matrix multiplication, right? So matrix multiplication is denoted, any multiplication is MATLAB is star. Okay, inverse A times B gives me that's how you solve the A and this matrix here. Then I have once I have A0, so I have A0 is 20, A1 is 0. That's why I don't have the term that contains T only, because A0, A1T, A2T squared. Okay, so this guy is missing here because A1 is 0. Then similarly, A2 is 11.25 and A3 is negative 1.875. Now I get my trajectory equation. So if I plot this, you can
go back real quick.
Yes, please. Yes.
I don't see how A3 is negative 1.87.
Yeah, if you solve that, you will get negative. Okay.
Well, you just times A3 by 1/848, or
no,
how's that done?
So you have 2 equations here. From this, if you solve this one, you get your A0 equals 20. This is very straightforward, right?
Yeah.
From here, you get A1 equals 0. This is very straightforward. Yep. Then you are left with these 2 equations. 4 times, not 4, even. This 1 and 20. So sorry. A1 and A0, A0, 4A1, 16A2, 64A3.
Oh, okay.
80.
Right. Yeah, I got it now.
Okay. So if you solve these 2 equations, then you happen to get.
Yeah, MATLAB would be way easier.
Yeah. So this is what you do, and then if you plot the trajectory, this is what it looks like. So we have the trajectory this, and if you have angle degree on the x-axis, which is Q, right? This is my Q is angle, and time t on the y-axis, then you get the trajectory like this. Okay. Similarly, if you do the velocity, right? We have the velocity also, right? So we have the velocity also. If you plot the velocity, so put the value of A1, A2, and 3A3. Then if you plot the velocity, then you happen to get the velocity like this. So the thing is, in the case of cubic polynomial, then you get the velocity of symmetric like this. Okay, you find the symmetric velocity like this, and trajectory angle variation with time looks like this in the case of cubing. This is typical. Even though I did this for a particular problem, this is true. This is for any problem which is
Do we have to do all three?
yeah. So yeah, we have to do all three. So depend, because if you have let's say you have all those constant, right? So you have how many constant here in total? 6. Then quadratic does not help, right? Because quadratic can handle just 4 constraints. Okay, so if you have 6 constant, then you have to go the other one. Maybe you might have to go the quintic here. Okay, polynomial having polynomial of order 5. If you have 6 constraints.
And how do we know how many constraints we have? Are we told that, or?
Now you have to, so do you, okay, yeah, that's important, because in the beginning, so how do you want your robot to move? So you want the robot to move from 0 velocity, or you want, or some, you know, what kind of situation do you want to have? Imagine what kind of situation you want. Okay, so you want the robot, okay, my robot has the initial position Q0. So this is always, almost always true, right? You have the robot from Q0 to, you want to move the robot from Q0 to QF. While moving from Q0 to QF, do you want the robot to move in this way? Meaning, let's say, do you want the robot move from 0 velocity in the beginning to the 0 velocity in the end? Or you want the robot to keep moving in the beginning and also keep moving in the end? What kind of robot you want? So most of the time you want the robot to stop in the initial point and stop in the final point also, right? In that case, you put B0 equals BF equals 0.
Then what are the other 2 constraints, since we have 4 here and there could be up to 6?
Yeah, because now if you want certain acceleration at the end, right?
Oh,
So you see
okay.
the acceleration. So if you want certain acceleration, then you might have to add this constant also. So position, velocity, acceleration.
Good stuff.
All right. Guys, unless you have any questions, I'm done for the day.
I think so.
Can we have a homework assignment on this instead of the one we have right now? I'm actually not kidding.
Yeah, I haven't done it yet. So, you know, we have to finish this first.
So can the other homework assignment not be worth that much and this one be a lot?
I don't promise it right now. I'll think
All
about
right,
it.
that's fine.
Yeah, I'll think about it.
All right, no, it's all good.
All right, guys. Thank you so much and stay safe.
All right, have a good one.
Everybody.
Bye.